Hey there, today we are going to look at lemurian crystals. Cool, huh? These are actually diamonds. They're long, thin diamonds, but that's what they are. And I know that because they scratch sapphire. And these are sapphires. These some bright boy got the idea that he could paint the back of these things silver, and they would be as sparkly as a diamond, huh? Pretty cool. And they are. They're sparkly as all get out, but they're still just sapphires. And you can tell because the color goes all the way across the stone, huh? It fills the whole stone up, and you can see that in a sapphire. That's what this is. This is a sapphire. I've got a place right here where I can blow that up. Whoa. Take my 9 on the Mohs scale of hardness little pick and go like this. Boom. Whoa. See, it just kind of skates around. Hey, maybe I should glue that. Very hard to do when you're doing it one-handed. Let's see if I can hold it in place. There we go. Little pressure. No scratches. No scratches. Okay. There we go. No scratches. And then I've got these guys, huh? These guys are the lemurian crystals called quartz, except, see, quartz doesn't have striations that go anything other than horizontal. And these aren't really long, thin crystals as so much as short, long, wide crystals. They go this way rather than this way. And this is a very sharp point right there. And I can go like this. And we just flipped it over because I put so much force on it. And let's see if I can get a reflection here. There it is. You can see the scratch right there. That's what I just did. The point of that thing left those 4 little lines across the crystal structure that weren't there a minute ago. Because this is indeed a sapphire, 9 on the Mohs scale of hardness, and that's how I determined that it's scratchable by the next hardness up. Okay, 10 on the Mohs scale of hardness is diamond. And it's about 100,000 times harder than this sapphire here. And this sapphire here is the hardest thing on Earth other than diamond. It'll scratch anything else on Earth except a diamond. Or, conversely, it cannot be scratched by anything else on Earth except a diamond. And so I have a whole bunch of sapphires that are painted silver on the back, and they're cheap. If you're interested, I've got a bunch of them. There's 10 per little packet here. 10 of them. And I will sell them. I bought them for $1 each, and you can have them for $2 each. Not per stone, per packet. These are a little different. They're actual real sapphires that you can mount and set and show people and say, wow, this is a cool yellow sapphire. And I'll take the scratches out. No worries. And I also, because we just showed that these lemurian crystals are in fact diamonds, because nothing else scratches a sapphire. So there we have a lemurian crystal. And I'm going to show you something here. This, right here, this point that where my finger is the top. That's where the lines of crystallization meet. Right there. There's I call them X and Y axes. In geology, we really call them alpha, beta, and gamma. Okay? But it means the same damn thing. It's like algebra, right? A, B, C. It doesn't matter what you call it. The idea is that they are a set of perpendicular axes to one another. That's what I'm getting across. And ABC or XYZ, it doesn't matter, man. So we will call them X, Y, and Z because that's what everybody knows. That's what everybody understands. When I say alpha, beta, and gamma, people go, oh shit, man, I don't know what that means. So we'll stick with X, Y, Z, okay? The X and Y axis are the two going side to side here, making the beginning of that termination. The long axis, right here, is formed by those two coming together. See what I mean? That's what that is. It's not like another plane within the... There's not 3 sets of planes. It's 2 sets of planes crossing each other. And the point where they cross is the z-axis. And what you're seeing there is not side-to-side striations so much as where the striations that go more this way. And let's find out where they are here. We can look at these and find them. That's what these are growth faces. This crystal was growing sideways, like this, and that's where it was growing, right there. And we can look at those, and it'll show you those planes within the crystal structure. That's what that stuff comes from. You can see them. There's 2 of them. And they meet up down here at the other end, right? So we've got a a point here. Now look where my fingers are. These are flat sides, and I'm looking down at a four-sided figure. 1, 2, 3, 4. And they meet at that point right there on top. And that's a little top of an octahedron, kind of stretched out because it had the opportunity to grow in that direction, as opposed to this direction. And diamonds are not relegated to one type of crystallization because they're cubic, and that means they go close-packed cubic. Close-packed cubic is the same, exactly the same, as close-packed hexagonal. Close-packed cubic starts here and goes down here, and they're little cubes all the way through this whole crystal because it's made out of little cubes of carbon. That's all it is, carbon. And they're smashed so close together they can share the bonds of the 4 outer valence electrons. Carbon is a semi-metal. It has 4 electrons in its outer valence orbit. When they get smashed together to make a diamond, they're so close that they can share that with each other. They can share that, and it becomes a double covalent bond. Covalent bonds are the strongest because they're sharing electrons, and that electromagnetic force holds them together and doesn't let them come apart.